Hello everyone, I appreciate the opportunity to be here to attend this conference. The title of our paper is FSE-MV Compressed Domain Video Information Assistant Hybrid Real-Time Vehicle Speed Estimation. My presentation will be divided into the following parts. First, background. Second, our method. Then I will talk about experiment. Finally, it is conclusion. Speeding causes the traffic accidents. Detecting of vehicle speeding is very important. Vehicular speed estimation is a vital component in ITS. Traditional speed estimation method is sensor-based. This method is costly and limited, and it needs surveillance camera support. With the development of computer vision techniques, video-based speed estimation was produced, but the method requires analysis of massive amount of data. It is too slow to detecting speeding vehicles in real time. It is unacceptable that the longer the vehicle overspeed, the more dangerous it will be. The steps of video-based speed estimation are as follows. The first is camera calibration. This step is divided into soft and hard. Stereo-based and coordinate system conversion are soft calibration. Marked areas and augmented lines are hard calibration. The second is vehicle detection and tracking. This step is often addressed by either modeling, background subtraction, or neural networks. Then it is speed estimation. Distance estimation usually using the Euclidean distance method. Time is obtained from the frame date. With distance and time, speed can be calculated. Step 2 vehicle detection and tracking is the most time-consuming part because they use the pixel domain method. Traditional pixel domain method require decoding and it detects the object from complete frame. The pixel domain approach has a high computational effort and intolerable latency. Compressed domain method does not require full decoding. Its information has less data size compared to pixel domain. It brings the possibility to increase the processing speed. However, the compressed domain information has lots of noise and lacks textual information. We therefore consider combining the strengths of both compressed domain and pixel domain information to achieve fast and accurate speed estimation. This is overview of FSE-MV. First, it is target segmentation. Step 1 is MV extraction and pre-processing. Then we get reliable MV to target detection and segmentation. ROI is determined and we get the pixel information in the ROI. Second, it is speed estimation. We're using ROI between multiple frames for tracking and open ROI pairs. The ROI pairs are one object in different frames. Next, it is future point extraction and matching. Only this part uses the pixel domain information. We are using matching point to calculate the pixel distance. Then it is coordinate transformation. Finally, we calculate the value speed. Next, we will introduce FSE-MV in detail. Step 1 is MV extraction. FSE-MV uses FMMPEG to extract MVs. In the coding standard, MVs are the smallest codes. Each of MV has one MV, and the MV has a horizontal parameter x and a vertical parameter y. The example is shown in the image. The MV size is adaptive. We normalize all MVs to 4 times 4. It provides convenience for processing. The example is shown in the image. All MVs of little MVs are given by large MVs. Step 2 is MV processing. We first utilize MV like 0 MV. 0 MV is defined as the MV which energy is equal to 0. MVs with 0 MV are skipped in the subsequent processing. The energy is calculated as in equation 1. MV spatial noise removal is for eliminating isolated MVs. Input is filtered MV field F. The example of SF as follows. We use the number of 0 MV in SF to determine the F. Like this example, we remove it. Output is MV field F prime. MV temporal noise removal is for eliminating fake MVs. Input is spatial noise MV field F prime. In the 3BF, in frame t-1 like this. In line 8, BF in frame t plus 1 is like this. At least one BF is not 0 MV. We consider F is real MV. Output is MV field F double prime, which is reliable MV. Step 3 is target segmentation. A binary map is constructed to isolate vehicles from the background. Reliable MV set to white in the map, like this. FSE-MV performs morphological filtering on the vehicle mask to remove voids or gaps, and then use connector content analysis to get ROI, like this. Step 4 is target tracking. Input are objects ROI and set of ROI in next frame. Output is tracking target. In line 2, we are using the projection MV to predict the position of the target in the next frame. The projected MV is calculated as in equation 2. We calculate the IOU of predict target to RI and find max value to get tracking target. In special case, IOU is 0. The center distance is used. The example of center distance method as follows. We find the minimum value to get tracking target. Next, it is feature point matching. We use the SURF, a common feature matching approach. SURF remains stable in translation and rotation. We use NNDR to get good match point. A target has many matches, and each good match will contribute to the speed estimation. Step 5 is coordinate transformation. FSE-MV uses the homography matrix for coordinate transformation. The matrix H is given in equation 3. We set as 3, 3 to 1 for H normalization. To solve for H, we obtained the following equation 4 and 5. The H may be obtained by 4 market points in advance. The coordinates of the matching points is in Li. The matrix H is for the frame. FSE-MV compensated the upper left corner of Li in frame for it, as shown in the picture. This is the matching point coordinate in Li. This is upper left corner of Li's coordinates in frame. We plus there, and then the coordinates after compensation can use H for coordinate conversion. FSE-MV uses equation 6 to get real-world coordinates. Calculate the object's value coordinates and tracking target's real coordinates respectively. Then we use the equation 7 to calculate real-world displacement. Next, FSE-MV uses trimmed mean to eliminate incorrect values. As shown in the picture, we sort the speed values and return the middle part of the value. Finally, we use equation 8 to calculate the speed. In the equation 8, n is the number of returned displacements. T is obtained from the frames per second. This is experiment part. We have a CPU environment and a GPU environment. Delay is defined as the mean estimation time required per frame. If the speed is within this interval, -3 to 2, we consider it is accurate. This is effect of noise removal. Different cases, FSE-MV can remove most of the noise. As shown in the picture, this is a no-vehicle case, this is a single vehicle case, and this is motor vehicles case. Experiments prove that our denoising method is effective. This is effect of segmentation. In a different case, FSE-MV has a good target box. The neural network approach uses pixel domain information for segmentation, and they have a more complete target box. However, FSE-MV has much lower latency than this method. As you can see from the table, our method is about an order of magnitude faster than the traditional pixel domain method. Neural network-based methods require more loading, and thus need more time for the startup as shown in the picture. This is speed estimation error distribution. As shown in the picture, FSE-MV achieves an accuracy rate of 93%. Also, it is not as good as YOLO or fast RCN. In small Earth interval -1 to 1, FSE-MV reached 52%. It is above YOLO and close to fast RCN. So FSE-MV has an acceptable accuracy. This is conclusion. We propose a hybrid method called FSE-MV that utilizes both pixel domain information and compressed domain information. FSE-MV is able to achieve an accuracy of 93%, with an overall estimation delay of about 32 milliseconds. Our future work is to explore the data available in the compressed domain, like residual data, DCT, and so on. Then we will improve the accuracy. This is references. That's all. Thanks for your attention.